Hey, Katie.
Hey, Ben.
What are we talking about today?
Today we're talking about SMOTE.
Smote as in the past tense of smite?
SMOTE as in synthetic minority something something. I need to find the tab open in my browser.
Ah, all right. Okay, well, while you hunt for that, I will say you are listening to Linear Digressions. Did you find your tab?
Yeah, it stands for synthetic minority oversampling technique.
Oh,
And,
there's no E at the end.
well, there's an E after in technique.
Oh, geez. Wait,
But
is it spelled with an E?
yes.
Oh,
Well,
I
I
hate it
guess
when
SMOTE sounds better than SMOT, right?
Smart, yeah. Okay, so paint a picture for me. What's the problem that this is trying to solve?
Yeah. So this comes to us a little bit from sort of your supervised classification realm.
Right.
And one of the things that can happen a lot in supervised classification is that let's imagine a case where it's just a binary classifier. So you have two different categories and you're trying to sort events into one or the other. And
Like, does someone have a disease or does someone not?
Sure, yeah. Or is this a fraudulent transaction or is this a legitimate transaction?
Yeah, you usually don't get half fraudulent transactions.
Well, exactly. Yeah, that's where we're going. Is that sometimes you're fortunate enough that things are fairly evenly balanced between the two classes, but very often this is not the case. One of the cases might be more interesting to you, and in particular, it might be less frequently found. So in this case, it would be someone who has the disease, because you could imagine a case in which many people get tested for a disease, but only some of them have it. Likewise, you can imagine that there are many more transactions that are legitimate than ones that are fraudulent.
Okay, so basically you've got a lot more of one thing, and not as much of the other thing. What's the problem with that?
Right. So if you're using one of the standard out of the box supervised classification algorithms, what very often happens is it's it can be a little too smart for its own good, and it'll just classify everything as the majority class. And that's not a crazy thing to do because it's kind of right. If you have
Oh,
something like
interesting.
99.99% of transactions are legitimate, then it's pretty easy for a classifier to say, well, let's just classify them all as legitimate because then I'm going to be 99.99% correct.
Oh my god, I guess that makes sense because it's optimizing for the highest accuracy rating or something like that. So yeah, in that case, it makes sense that it's not weighting the fraudulent transactions as heavily as it's weighting the non-fraudulent transactions in the way it's searching.
Yeah, so classifying everything as the majority case is not a crazy thing to do. On the other hand, you can see how that's not particularly useful to you if what you're trying to do is actually find the people who have the disease or actually find the fraudulent transactions. So, first thing that we should point out is that this is one of the reasons that you need to be a little bit careful sometimes with which metric you use when you're trying to optimize these machine learning algorithms. So accuracy is one of the classic ones that can make you feel really good if you have imbalanced classes, because a lot of times it'll tell you, I'm just going to classify everything as the majority, and then the accuracy looks pretty good. Other metrics like the area under the ROC curve are not always as prone to this problem. So first thing is, if you know that this is something that you're dealing with, think a little bit about the metrics that you want to use and don't let accuracy give you a false sense of security.
Okay.
So second thing is, now what do you want to do about it if you have this problem?
Right. Yeah, that was my next question.
Yeah, so a few different ideas, and we'll get to SMOTE in a second, but some of the things that are a little bit simpler and that work not too badly. So one is that you can either upsample your minority class or you can downsample your majority class. So you can artificially get rid of cases of the majority class so that you end up with something that's a little bit more balanced, although smaller. Or similarly, you can say if you want to have 10 times the statistics for your majority class of what you have right now, just take each of those rows in your minority class and enter it into your training set 10 times or something.
Oh, so basically just duplicate your data.
Yeah. And there's different people who've done different investigations of exactly what's the best way to do the upsampling and downsampling, but that's the basic idea. Another thing you can do is sometimes these algorithms will support different weights for different kinds of mistakes that the algorithm could be making. So you might say something like, if I let a fraudulent transaction go through, that's one kind of mistake.
Like, that's really bad.
Yeah. If I accidentally take a legitimate transaction, I block it, that's a different kind of mistake. And maybe the costs for those two mistakes are not the same. So maybe the typical cost for letting a fraudulent transaction go through is $1,000, and the typical cost for accidentally placing a hold on what was actually a perfectly fine transaction is $10. So I'm willing to make 100 of one kind of mistake for 10 of the other.
Of course,
or
unfortunately,
for one of the other.
Unfortunately, banks will not factor in the user's frustration in any way other than just as some kind of monetary value of how likely maybe they are to close their account or something.
That's probably right.
So, yeah, that's a bummer.
Yeah, but a lot of these algorithms then, what the inside of the algorithm is trying to do is it's trying to optimize some kind of cost function or maximize some kind of benefit that it's calculating. And so then you can incorporate those weights into that function, and then it will learn to kind of err maybe more on one side or the other, and that can help you give yourself a little bit more of a handle for saying, no, it's very important to me that I not make the mistake of missing my minority class examples when they show up. So that's
Right.
another thing you can do.
Yeah, it sounds like although a lot of these algorithms can be very powerful, even just right out of the box, they do make certain assumptions, and this is maybe one of the assumptions that a lot of them make. And it's really important to know what those assumptions are going in before you use something, and then you get burned.
Yeah, so what you mean is that the naively out of the box, these algorithms will treat all kinds of mistakes as kind of equally costly, but that's not necessarily always the case. Okay, so those are two different things that we can think of off the top of our head: over undersampling and changing around the class weights. SMOTE is something that's a little bit different, and it's kind of cool, and it seems to, at least in the cases that I was reading about in this paper, it seems to usually work better than either of those two things. And so the idea of SMOTE is a little bit hidden in the name, synthetic minority oversampling technique.
Synthetic minority oversampling technique. So it's a technique for synthetically oversampling your minority class.
Yeah, that's fair. That's fair. So we're starting with the idea of oversampling. So we want to generate for ourselves extra examples of our minority class. So we want to boost the statistics of the sample that we have available to ourselves of the minority class. And a simple oversampling would be, I'm just going to repeatedly train over and over on the same examples. And, one of the things that can result when you do this is that your algorithm just learns very specifically what your minority class examples look like. And so it just drills down into those little pockets of things and says, like, this is definitely minority. And it hasn't learned anything that's very generalizable. It's just really memorized, these few examples that it has to learn from.
Yeah, so it says, yes, when I see a Home Depot transaction for $47.16, I know that one's fraudulent.
Yeah, especially if it happens on a Tuesday and the area code starts with a 3. Yeah, it can learn all kinds of wonky things that are not particularly insightful, but that can make it think that it's very smart. So what you want to do is you want to give it more minority cases, but ones that look similar to the ones that you're sure of, but not exactly the same.
So like representative, but not duplicates.
Exactly. And so the S in synthetic is we're generating these synthetic minority examples that are sort of inspired by our real minority examples, but don't look exactly the same way. And here's the way the algorithm works. You have your real actual cases of your minority. So these are going to be coming from your training set. And for each one of the minority cases that you have, you're going to take that sort of point in space, and then you're going to find its 5 nearest neighbors that are also of the minority class. Then you're going to randomly pick one of those 5. And this 5 is the number that they used for this particular implementation, but you can imagine that's kind of a free parameter. But just go with me here. So
So
Okay.
the picture in my head is I've got a point that I'm thinking about, and then I look at all of the points around it, and I find the 5 points that are closest to it in this kind of like almost like a scatter plot is what I'm seeing in my head.
Yes, the 5 points of the same class. That's right.
Got it. Okay.
And
And these are all the fraudulent transactions or the people who were diagnosed with the disease.
Exactly. So you have these 5 extra points that you've identified, and you randomly pick one of them. Mm-hmm. Then you can imagine almost a line segment that connects sort of your original point and then the one of the 5 that you've picked.
Okay. So I've got a line.
And that line is going to have a distance and it's going to have a direction. And what you then do is you randomly pick a number between 0 and 1. And you imagine that random number is kind of a slider that goes along that line segment. So if it's 0, it's maybe all the way at the original point. If it's 1, it's all the way at the point that you've selected as its pair. But it's going to be random where along that segment it goes.
Okay.
And so
that's my new point.
That's your new point, is what's given to you as the point along that line segment by this sort of random multiplier.
So if I want to generate a whole bunch of new points, then I can just do that over and over and over again. And none of the points are really going to be the same as any of the original points. They're going to be very representative, though, because you're taking 2 that are close to each other and you're putting you're putting another point somewhere randomly in between those 2 points.
Right, as kind of a compromise between these cases that you know are true minority cases. You're going to come up with something that hopefully looks something that's in between them, literally.
And the reason I imagine that you want to do something like 5 points, the 5 nearest neighbor points, is if you just do the closest point, then you're going to basically be drawing points along the line, along one straight line, or, some kind of lightning-like shape or something like that. It won't necessarily be as representative within the space.
Yeah, so you want to inject some randomness in all the ways that make sense. So one of the things is, let's say you want to upsample your minority class by a factor of 10. So you don't necessarily want to go up to, or you might be fine going up to the 10 nearest neighbors, but you could imagine that maybe the 5 nearest neighbors are actually going to give you something that is reasonably consistent with your original point. So you want to try to keep the number of nearest neighbors kind of under control. But at the same time, if you have 10 synthetic data points that you're trying to generate and you're only taking, let's say, this point and it's 1 nearest neighbor, then you're just going to get a string of points like along this line segment that connects them, which is kind of weird. That doesn't really look like real data, quote unquote. You're trying to come up with something that's a little bit of a compromise between the patterns that are introduced by this generating process and the fact that that generating process is also hopefully giving you something that looks reasonably like actual minority case examples. So you're a little bit walking a line here between something that looks a little bit too synthetic and something that looks too random. But yeah, they did a lot of studies basically of this upsampling technique, which with a number of different real world data sets to try to see if this was an effective way versus something like upsampling or changing the weights in algorithms, and found that in not literally every case does SMOTE do better, but in most cases and for most algorithms, at least of the ones that were investigated by these researchers, it seems to do quite well. And conceptually you can see how it has some nice features relative to some of the other options.
Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.